Okay, so I think we might all be able to agree that we could probably spend hours talking about ratio and proportion concepts and related concepts. And since we don't have that kind of time today, we'll focus on just a few areas. Now, I had a lot of information in here to start with, and I really had to pare it down. So I hope we'll still stay close to the 30 minutes. And so I had to pick and choose what we were going to talk about today. And I apologize if it at all seems like I'm jumping around as we go through. But as I said, there's so much to cover and we can't hit all of it. So today we'll talk about the importance of proportional thinking. We'll talk about types of ratios. We will look at strategies for solving proportions. We'll solve a few proportions and a few percent problems, and we'll look at an exploration type of activity for proportions. So let's start out with a definition of proportional reasoning. Now, according to the book, Elementary and Middle School Mathematics, Teaching Developmentally, proportional reasoning goes beyond the idea of setting up a proportion to solve a problem. The authors say that it's a way of reasoning about multiplicative situations. And this is very important because ratios and proportions both involve multiplicative comparisons. They also state that proportional reasoning is considered a unifying theme in mathematics. And they state that it is at the core of many concepts like similarity, dilations, scaling, pi, constant rate of change, slope, speed, rates, percent, probability, and more. So it's in so many areas, which is why we can't cover it all today. And unfortunately, according to the authors, more than half the population of adults are not proportional thinkers. And they say that this is a result of focusing too much on solving missing value proportions, which I'm sure we all use. I'm guessing we all use. So how do we then develop proportional reasoning if we're not going to use just the missing value? The authors suggest that proportional thinking is best developed through activities and experiences that involve comparing and determining equivalent ratios and solving proportions in a wide variety of problem-based contexts and situations through reasoning, not through the rigid use of formulas. Before we look at some examples of problems and how we can work on that type of thinking, let's take a quick look at the different types of ratios. We have the part-to-part ratios that relate part of a whole to another part of the whole, like 5 circles to 4 stars or 5 to 4. And some examples of where we see this type of ratio are in circumference of the circle to the diameter, the ratio of rise to run, and the odds of an event occurring in probability. The next type of ratio is part to whole, which relates a part of the whole to the whole amount, like 5 circles to 9 shapes, or 5 to 9. And a few examples of that type of ratio are percentages and probabilities. And then we have ratios as quotients. So if we have 4 oranges for $5, we can divide to find the unit rate of $5. 5 to 4 gives us $1.25 per orange. And then there are ratios as rates where we're comparing quantities with different units like miles per hour, pencils per box, and inches per foot. So we've got all those types of ratios. Now, when we're working with students and ratios in 6th grade, I'm guessing this is the same for you all who teach 6th grade, we normally begin by naming ratios, like the circles to the stars or the stars to the whole number of shapes, and then finding equivalent ratios. And sometimes students have difficulty finding equivalent ratios, especially when they're looking at a proportion with a missing value, because they often want to add, like from 5 to 10, we add 5, so we should add 5 to the 9. We can tell them it's like finding equivalent fractions and that we can multiply, but sometimes they just do get stuck. And we're going to stop and take a second to look back at the problems we started with. And it might not seem like this is connected, but you'll see where I'm going. So the first problem said, and if you didn't get to read this as we were warming up, then you can read them with me now. Manny and Jamal both ran to the park, each at the same rate. Manny started first. When Manny had run 5 blocks, Jamal had run 2. How far will Jamal have gone when Manny has run 10 blocks? And don't give me an answer. Don't give me an answer. I just want you to think about it. So I'll give you like a few seconds just to think about that in your head, and then I'll read the next one. It's hard for me to be quiet. Okay, Manny and Jamal both ran to the park. They started at the same time. When Manny had run 5 blocks, Jamal had run 2. How far will Jamal have gone when Manny has run 10 blocks? They seem like very similar questions. Looking at problems like these, it can help students start to see the difference between an additive relationship and a multiplicative relationship. Do both of these show a multiplicative relationship? No, they don't. The first one shows an additive relationship. Since Manny started first, he was 3 blocks ahead by the time Jamal ran 2 blocks. So if they continue running at the same rate, he will continue to be 3 blocks ahead until they finish. So by the time Manny has run 10 blocks, Jamal will be at 7 blocks. And we could write that as an equation to show students that Manny will be 3 blocks ahead if they both stay at the same rate. So that's additive. The second problem is multiplicative. They leave at the same time, but Manny is running faster. So when he's gone 5 blocks, Jamal is at 2. When they each continue at their own rates, Manny goes in 5 blocks. Jamal, another set of, which puts him at 4. So the first example is what students often want to do when they're looking at proportions with a missing value, at least in my experience. Not all of them, some of them. If we set this up as 5 to 2 is equal to 10 to something, some students will do exactly what we said. They'll say, well, I added 5 to get to 10. So if I add 5, that's going to get me to 7. So I'm missing number 7. Yeah, the missing number is 7, but that's not how the proportion is supposed to work if we're looking at a multiplicative situation. So it's situations like this that the authors suggest students have experience with in order to start working on that proportional thinking. How do we get them to develop the multiplicative thinking? Finding equivalent ratios and solving proportions correctly and well. We can help them become more accurate and more flexible and good at these things by using a variety of strategies. There are several strategies we can use, and one of the most commonly known one is the cross products, most commonly known not for developing the thinking, I'm sorry, but for solving, is the cross products. According to the authors, this is something that should be introduced after other strategies because it is the most abstract and the least intuitive. So I probably have this organized a little incorrectly because I was going quickly here. So this is a common method, but it's not going to help them as much with their multiplicative thinking. That should be introduced after things like rates, finding rates, scaling, tape diagrams, double number lines, and using ratio tables. So let's take a few minutes to look at some of these strategies. That's what we're going to focus most of the rest of our time on. As I mentioned, again, we could spend hours on this. So we'll just try to hit some important ideas. We're going to start with a very simple strategy for finding equivalent ratios, which was not on the list, which is drawing representations. Especially in 6th grade, I like to have students draw the representations. And I use the phrasing, for every 3 circles we have, there are 2 stars. For some students, saying 3 to 2 isn't enough. I think adding the we have helps them understand just a little bit better. I think there's just something weird just saying for everything that we have this. Maybe it makes it a little bit more real. It's more of a complete sentence. I don't know. But I like to say for every this, or every time we have this, then we have that. And so then they physically would draw for every 3 circles, we have 2 stars. For every 3 circles, we have 2 stars. And then they can count and say, if we have 6 circles, how many stars were we looking for? If we have 9 circles, how many stars would we have? And we can use the physical drawings to set that up, or you could use manipulatives as well if you have enough great things handy for students. And then we can look at those new ratios and look at how we would multiply to get from 3 to 2 to 6 to 4, or from 3 to 2 to 9 to 6. So that is our first very basic strategy that helps develop that type of thinking. Another great strategy that makes the relationship visual for students are the tape diagrams. All right, so we're going to use a very simple example of for every 3 dogs, there are 5 cats. And we can show that with our tape diagrams by 3 blocks for dogs and 5 blocks for cats. And we may even find we use the tape diagrams differently depending on what you and I do and how you and I think. So we might use them a little differently than each other. So then we can answer a question like, if there are 15 cats, how many dogs are there? Now, if we take our 5 blocks for cats and we say we know that is now worth 15, then we can take those 5 blocks and split them up and find that each one is worth 3. So we've got each block represents 3 cats, and that would be the same for the dogs. And so that would lead us to the fact that we have 9 dogs if we have 15 cats. We could also use the tape diagram to work with a situation where we're given the whole amount and we need to find one of the parts. Like if there are 32 pets, how many dogs are there? And so here we've got 32 pets total, that's our whole. And we now have 8 blocks in our whole to make up the 32. And so each block now becomes worth 4 because 32 divided by 8 is 4. And we can see that we have 12 dogs, and that would give us 20 cats. And we can even, we can look at that multiplicative relationship. We can look at our original 3 dogs, multiply it by 4 to get 12. Our original 5 cats, multiply it by 4 to get 20, and reinforce that multiplication idea that way. And we can also use it for a problem like this. There are 10 more cats than dogs. How many cats are there? And here we've been given the difference between the number of pets. And so we can see the difference between them is 10. So these 2 blocks are as a total worth 10. Each one would then be worth 5. So our blocks are all worth 5, showing us that there are 15 dogs and 25 cats. And we can double check that again. We can say, wow, my brain just went dead for a second. 3 times 5 is 15, and 5 cats times 5 groups of them is 25, and 25 minus 15 is that difference of 10. All right, another strategy we can use is double number lines. Now we won't go through all of those examples, but we'll look at one example. We'll keep the basic ratio of for every 3 dogs, there are 5 cats. And then we'll look at the question, if there are 15 cats, how many dogs are there? So we can create our number lines as fancy as we like or simple as we like, label them dogs and cats, put the initial ratio values on there. So we had 3 dogs, 5 cats, add a few more parts to the number line. And then we can see how these numbers vary together. So we can say with 10 cats, we would then have 3 more dogs. So 5 more cats, 3 more dogs gives us 10 and 6, 15 and 9, and so on and so on. So students could see those relationships and as they change on the number line. All right, another strategy is to use ratio tables. These are also a great way to show proportional relationship between ratios, and they're excellent for keeping our values organized. So if we have this situation, we have this ratio table, and this is already created. This isn't something that I'm saying here's the problem created. It's already created for us. We have the number of hours worked and the amount of money earned. And if we look at this and we see somebody is making $17 for 2 hours, We could use the ratio table to find the unit rate of $8.50 per hour. So they're working 1 hour, they make $8.50. And then we could use it to find other missing values. So if we want to know how much they earned for 10 hours of work, once we've got that unit rate, then we can find that they multiply by 10 and we find that they have made $85 for 10 hours of work. Or if we want to figure out how long they worked for 110.50, then we can divide and find that they would have to work 13 hours. We can then use them to solve percent problems, ratio tables, and double number lines. For this example, we have Kathy's order at the diner costing $12.75. She has to pay 6% tax on the bill. How much is her tax? Now, of course, there are so many ways we can solve, but we're going to start with the ratio table. We can put in the table, we've got percent and tax. We can put 100%, 6%, and 1%. 100% because we can start with that amount. That's what we're starting with. We know that one. We know 100% is $12.75. If she had to pay 100% tax, she would pay $12.75. And then we can take that and find what 1% would cost by dividing by 100. And there we've got that. And then to find the 6%, we multiply the unit rate by 6 and we get 765 thousandths, or she would pay 77 cents. If we wanted to use the missing value proportion to solve this, we would set it. Now, this is how I set it up with my students sometimes. Percent over 100 equals is over of. And I always label the part and the whole. So if you were using this one with students, we would then put the 6 where the percentage is what we're looking for. What is 6% of the bill? And then 1275 is our of. We are finding 6% of 1275. And then cross multiply and find the same answer. Now, if students looked at both of these methods and compared them, they might notice that in the ratio table, they divided by 100 first and then multiplied by 6. Whereas in solving the proportion for the missing value, they multiply by 6 first in the cross multiplying, and then they divide by 100. And this is why it's so helpful to have multiple ways, exactly, depending on the student, Christy. When we've got the multiple ways and the different things to show students, then they can take what makes more sense to them, okay? But the thing I like about the ratio table is I think it does a little bit better show the relationships between the percents, just a little bit differently than the proportion might. All right, let's look at another problem. We have Mandy bought a pair of jeans on sale. The original price was $32.95, but the jeans were 20% off. How much did Melissa, I changed the names, how much did she save? For this problem, we could take the 100%. Yes, absolutely, Shelley. The 100% and organize the table going by 20% because we're looking for 20%. So we could put all of that into the table. Now that gives us 5 sections. So we can divide $32.95 by 5. So our 20% would be $6.59. And then if we wanted to know the 40 and the 60 and the 80, we could add those in as well. But again, we're kind of showing the breakdown of the 100% into sets of 20 and finding their discount there. We'll look at another example, this time with the double number line. Chris sold some birdhouses he made. 80% of the sales will be profit for him. If he sells $150 of birdhouses, how much will his profit be? So we'll go with the double number line, as I said, setting it up as percent and profit. We'll split the percent number line up into 20 to 100. And we will put the same number of lines on our profit line and add our 150 under the 100% because 150 is how much he sold. That was the money he got. That's 100% of the money he got. And so now we are looking for 80% of the sales. So again, as in the previous problem, we can divide the 150 by 5. So that 20% is $30, 40% is $60, 60% is $90, and 80% is $120, and that is his profit. So I like the double number lines with breaking up the percents like this and breaking up those amounts for students. And we can set that up any way we want. If we want to go by 10s or 5s or 50, well, you don't have to do much for 50, but 25s, we can the problem. And we can use the missing value in the proportion, if we want to do it that way, putting 80 as the percent that we're looking for, 150 as the amount we're finding 80% of, and then solve by cross multiplying. Another way I show students, and you probably do this too, is to use the equation percent times the whole equals the part. And then we can substitute what we have into that equation. So in this case, we would change our percent to 0.8, and multiply by 150 to get our part, which is what his profit will be, and that is $120. So those are just a few examples for percent. We, of course, could do so many more, but we'd be here for forever. So I'm just going to quickly look at this proportions lesson that I'd like to share with you that I think is fantastic and students love. This is a lesson I found many years ago through Mathline Middle School Math Project, sponsored by PBS. As I said, students really like this. So this ratios and proportion lesson presents the students with an environmental problem. Scientists have determined that the number of fish in the Chesapeake Bay has decreased. Assuming this is true, scientists must have counted the number of fish and noted the change. How did they count the fish? So we start out by brainstorming the ways that scientists could count the fish. And every year, I usually have 4 or 5 math classes. For a long time, I had 4, then I had 5. Every year I used this lesson, there was always a student who would say that the scientists could tag the fish. So they had somebody in those classes had the understanding of what that meant. And then we would discuss what that means, how tagging the fish would work, and we talk about the capture, recapture method. So for this lesson, we used goldfish, regular goldfish crackers, pretzel goldfish crackers, 2 paper bowls or any kind of container that can hold things and that students can scoop with. We would use our second bowl to put the captured fish in, and then a spoon just to be able to scoop. Now, when I did this, I didn't really count the number of fish I gave each group. I simply poured fish into the bowl, but they all ended up being around 70-ish. Now, before students would actually get started with their procedure, I would absolutely demonstrate all of the steps for them so they understood exactly what to do. And then I would give them a recording sheet that also included their directions. And so here is what they would do. They would capture a sample of regular goldfish from the bowl. And then they would tag them by replacing them with pretzel goldfish. So they would, if they pulled 7 out, they would set those 7 to the side. They would no longer be part of the fish population. And they would put 7 pretzel goldfish in there instead, so we could tell which ones were tagged. And then they would put the tagged fish back into the bowl, mix them all up so that they were tagged and they were evenly distributed. Their next step is to capture a new sample. And on the recording sheet, record both the total number of fish in their sample, so 10 fish, and the number of tagged fish in the sample, maybe 3. And then they return all of those fish into the container. So they record those numbers on the sheet and then put all the fish back. And then they repeat that process maybe 6 or so times. We had 40-minute math periods, so that's what worked for us. If you have longer math periods, you might be able to do more than 6. And then when they're finished, we guide the students to create and solve a proportion to figure out how many fish were actually in their bay or in their bowl. Now to do that, you can see the recording sheet down here. They had to find the average number of tagged fish in their captures and the average total number of fish in their captures. So they needed that. So we worked on that together. So the proportion we guide them to is the average number of tagged fish to the average total is equal to the number of fish tagged to the total of fish in the bay. So then they calculate their averages and they add the number of fish they actually have tagged in their sample, and they can figure out the total fish in the bay. And yes, I will include this stuff in my replay. Okay, so after they calculate the number of fish in their bay using the proportion, we actually have them go ahead and count how many fish were in their bowl or in their bay, so they could see how close their estimate with that proportion came to their actual population. Now, some of my groups did get pretty close to the actual number in the bay. I do have this in a blog post that I wrote about this one year, and the closest I think I had was 68 was the estimate from the proportion, and 74 was the actual number of fish. So it's not too far off. It did seem that groups with larger sample sizes ended up with closer estimates than the ones with smaller sample sizes. So you might want to give more fish than I did, which was, as I said, about 70-ish. But it can also, the estimates can also depend on how careful the students were with this whole process, how carefully they were scooping, counting, everything. They weren't quite as scientific as a scientist would be. But this is a great activity to show students a real life application of proportions.